Okay, everybody. So we're just going to quickly go through this question here. It says a metal rod is being carried down a corridor p meters wide. At the end of the corridor, there is a right angle turn to another corridor that's q meters wide. What's the longest rod that can be carried around the corner horizontally in terms of p and q? So I've got it drawn out here and sort of how I'm going to use my angles here, my theta. Now, technically speaking, what I'm actually doing is minimizing the total of lengths x and y. And if in your head here you kind of rotate that blue line there around that corner, you'll understand why it is that I'm actually minimizing that length there. It's just that when we talk about it, when you visualize yourself walking down the hall, that rod doesn't change lengths here, and so it makes more sense to think about it as what is the longest rod that I can use here. In any case, let's just put this out here. This is going to be the sine of theta is going to equal p over x, which means if I look for x all by itself, that's going to be p over sine of theta or p cosecant theta. And I can do the same thing down here. That's going to make that cosine of theta will equal q over y. And I'll just take a really quick jump here. So it's going to be q secant theta. So when I put these together now to get my z, I am going to get p cosecant theta. Sorry, I think I put an x over there. Should be theta. And this will be q secant theta. And now when I take my derivative, I am going to get negative p cosecant theta cotangent theta plus q secant theta tangent theta. And what I'm going to do is I'm going to set that equal to 0 because I'm looking for that minimum. Okay, and when I do that, I will get p. I haven't really done anything at this point. I'm just going to write this out here so it's equal to 0 so that step is clear. And then I'm going to bring everything over that's negative. So it'll be p cosecant theta cotangent theta equals q secant theta tangent theta. And the beautiful thing about this is I'm going to bring the cosecant theta cotangent over through division. And when I do this, and this might take you just a couple of moments to see how this is working here, but I'm actually going to get tangent cubed. Okay? Secant divided by cosecant is tangent. 1 over cotangent is tangent, and then I've got a cotangent sitting there. And so now I'm going to get that tangent of theta is equal to the cube root of p over q. Now, what I'm going to do at this point right here is I'm going to look at that in terms of a right angle triangle. Here's my theta. I'm going to interpret this as this being the cube root of p and this being the cube root of q. Okay? And so then here's my hypotenuse. And I know that when I put that together, that is going to be the square root of the cube root of q squared plus the, I'll just do it like this, cube root of p squared. Just using the Pythagorean theorem there. So now z, now that I've got that, I can go back and I know that z is supposed to equal p cosecant theta plus q secant theta. Well, that's going to be p. Well, cosecant is going to be the square root of the cube root. And actually, I'm just going to write this as a fractional exponent. This will be 2/3 plus q to the 2/3, okay, over the cube root of p plus q. And secant is going to be the square root of p to the 2/3 plus q to the 2/3 all over the cube root of q. And I'm just pulling the cosecant of theta and the secant of theta from this triangle over here. So now I've got this common square root of p to the 2/3 plus q to the 2/3, and that's going to leave me with p divided by the cube root of p plus q divided by the cube root of q. And that is going to be, well, p divided by the cube root of p is going to be p to the 2/3. Q divided by the cube root of q is going to be q to the 2/3. And notice what I've got here. When I put that all together, I get p to the 2/3 plus q to the 2/3. The bases are the same. This becomes to the 3/2.